Hello everyone, welcome to this session on kinematics of machines. In this session, we will be looking at computing the velocity and acceleration of links in a mechanism via Python. We will take up the analytical equations that we derived in the previous session and we will simply code these equations into Python to obtain the velocities and accelerations of different joints or links in the mechanism.
Let us have a quick recapitulation of the algebraic approach that we used to solve the 4-bar mechanism. So if you remember, there was a 4-bar mechanism, something like this. And in this 4-bar mechanism, so these were my link lengths A, B, and this was C and D. And what we did, right, initially we treated all these link lengths as vectors. So this was my A vector, this was my B vector, this was my D vector, and obviously this was my C vector. Now this was at any instant of time making an angle of theta with the positive x-axis. This was making an angle of phi with the positive x-axis, and this was making an angle of beta with the positive x-axis. Now we defined the vector loop equation. Alright, so this is also called as loop closure equation. So this was something like this: A vector plus B vector minus C vector minus D vector. This was equal to 0. So now we will see that how can we solve this one via Python. So if you carefully remember what I did, I simply expressed this entire thing into complex format. So this was my complex number format. So C vector C to power I, this is I beta, and this was C to power E5. And obviously D vector will be equal to D e to power I0. So this is simply equal to D itself, right? After this, if you remember, we separated out this entire part into a real and imaginary parts and formed two trigonometric relations. But this we are going to do via Python. We will see that via Python we can entirely automate this analysis, right, to compute for the desired linear angular velocities and desired linear angular accelerations in this 4-bar mechanism.
To begin with, we will first install Python in our PC. So you simply go to your Google Chrome browser and simply type download Python. Now you simply go to this website and just click on this download Python install manager. This will do the job for you. Now I'm using the Visual Studio Code editor, right, for typing my programs. So here you can simply type Visual. So let me just show you. You can simply type download Visual Studio Code. So you simply go to this website, right? And now you have a link. You have an option to install this VS Code editor, right? Either on Windows 10 or 11. So once you click on this will install the editor for you. Once you install VS Code editor, right? So this simply creates a shortcut, right, on your desktop, or maybe you can go to this search setting and simply type Visual Studio Code. So from here you simply click on open. Now this will open the VS Code editor for you. Now you go to file, click on new file, and then you have an option to select, right, text file, Python file, Jupyter notebook. So as per my convenience, right, I am simply selecting this Python file. So it's up to you what you want to select. Now there is a catch here. In case if this Python file you are not getting this option, so simply click on extensions and simply type python Python here. So once you type Python, now you have this, right, Python extension published by Microsoft, right? So you simply click on this and install this extension. After this you will get this option Python file. So now let's go back to this file option, then click new file, then just select Python file, right? After this it is better, let us toggle this panel. So now we will start coding all the equations, right, that we saw in the previous session. So let us begin with, before this let me give it a title. So I'm simply giving it a title: analytical analysis of a 4-bar mechanism. So obviously, the first thing that needs to be considered is that which libraries we are going to use, right, to solve this problem. So here we will basically use two libraries. So one is import NumPy. This is one of the library, right? So this is, as most of you might be familiar with this, NumPy is a library for basic calculations, basic statistics, right? Now here we will use another library which is actually very helpful when you have functions involved in your analysis. So here I'm going to take this library which is called as import Sympy, right? And then I'm simply typing import Sympy as SP. This is also import NumPy as NP. Let us type this. To access this Sympy library, what you do, you simply go to your command prompt and simply type here pip install Sympy. Now it's very important to note down at this point, while installing Python, just remember that you have to tick mark the option allow pip to access the path environmental variable, right? So this is a very important thing that if you don't do this, then this pip install may not function properly. So just keep in mind that while installing this Python, right, you are given an option allow pip to access the path environment variable. So you have to simply tick mark that option. Now once you install the Sympy library, after this just go to your Python editor, right? Now here we will start with first defining the links. So let us define the links. So AB, let us say AB is my input link, then BC, which is obviously the length of BC is B, and this is my coupler link. So we are exactly following the same notations that we have used before. So this is my coupler link, then DC is C, the output link, and then finally we have AD, which is D, fixed link. So after defining this, the next thing that we are going to do is simply form the vector loop equations, right? So let us see this. How can we define or form the vector loop equation in Python? So this is quite obvious. So we will simply define a function, define vector loop equation. Let me name this function as vec underscore loop underscore eq, and then this is theta comma beta comma phi. So we are already aware that the two equations, right, they are functions of the three angles theta, beta and phi. So now we will define this function in terms of theta, beta and phi. Now let me write down that equation. So it is basically VLEQ, that is vector loop equation. So I'm simply using some notations to describe the equation. Now it is small a, that is the link length, multiplied by sp dot exp. Then in the bracket you have again sp dot iota, and then multiplied by theta. So if you remember what I am trying to do here, right? So I am trying to write the entire equation in complex form, right? So this is one of the benefit of using the Sympy library. So if you have Sympy library, it is actually possible to define the vector loop equations as it is. Now after this, you simply type plus p multiplied by again sp dot exp. So this is the exponential part which I am representing. Then what? I multiplied by beta, right? And then you have minus c again sp dot exp, then sp dot I ph 5, then minus d, right? So here we have defined the vector loop equation exactly in the complex form that we saw before. Now this is obviously nothing. This is, if you carefully observe, this is a vector plus b vector minus c vector minus d vector. Clear? Now sp dot I, it simply represents the complex notation iota, right? Now after this, let us break this equation into trigonometric form. So this is what we were doing before also. So we will simply break this into trigonometric form. If you remember, when we were doing this manually, right? So this was the second step. Only thing, right now we are simply starting with the complex equation so that we can entirely automate this program to compute the velocities and accelerations. So here we have complex, then we have VLEQ. Now what this is going to do, this sp dot expand under complex, it will simply expand this complex equation VLEQ into trigonometric form, right? So this is equation under trigonometric, that is sp dot expand underscore complex, in the bracket you have VLEQ. Now let us separate out the real and imaginary parts from this trigonometric relation, right? So we will write down equation underscore real is equal to sp dot re, and then we have equation under trig, right? Then again we have equation, that is the imaginary part of equation, so it will be simply sp dot im, and then eq underscore trig, that is the trigonometric equation, right? So this is my real part, just remember this part. This is my real part and this is my imaginary part. Now after this, we will simply end this function. We will simply type return equation underscore real, comma equation underscore imaginary. So after we have formed our vector loop equations, let us go ahead and let us simply start with the position analysis. So when I say position analysis, we all know that I am talking about computing what? Computing the angles beta and phi when the input angle theta is provided to us. Now in the position analysis, what we will do? First, we will simply define this A, B, C and D as symbols. So to do so, what I am going to do, I will simply type sp dot symbols. Then here you have the inverted commas A, B, C, D, and then we know that all this link lengths A, B, C, D, they are real numbers. So we will simply type real equal to true. Now again, this theta, beta and phi, again we are going to define these angles as symbols, right? Now just note it down here that for now we are provided with the values of link lengths A, B, C and D, right? So it is always better to treat this theta, beta and phi as symbols, and obviously you can treat these values for now as real numbers. So we will say theta, beta comma phi is equal to sp dot again symbols, and then here you have theta, then beta, phi, and again we will simply declare that these are real numbers. So let me just write it down here. Define angles as symbols and real numbers. So once this is done, let us define this term iota also. So I am simply calling it as iota only. So this is nothing. This is sp dot I. Now just access the displacement equations or the position equations from this definition. So let us access these equations. So we know that, right? So these two equations will be required to solve for the angles beta and phi. So let me just type it down. Equation underscore real, comma equation underscore imaginary. This is nothing. Now once you have defined the equation, you can simply take vector loop equation, and then here what you have, here you have theta comma beta comma phi. Now the displacement equations are available with us, right? So the next step is to simply substitute the values. So I will simply define a dictionary of different values that we need to substitute into the two equations to calculate angles beta and phi. So let me just define it. So first we have values. So let's go one by one. So we will simply say A is 50, B is 66, C is 56, and D is 100. So just keep in mind that all these values I am taking from the previous numerical problem that we solved. So theta is equal to np dot deg degree to rad radian, and then what angle we have been given an angle of 60 degree. So it's very important to check it out here that before substituting this theta into these equations, into the above equations, it is important to convert the degree values into radian. Then after this, just put a comma sign here, B, C, and then D, and then what you have, theta, then just close the brackets. Now after the values are defined, the equations are defined, let us solve this. So for solving, what I am going to do, so I am using this sp dot solve command from the Sympy library. So here what I am going to do, first I will substitute these values. So let me just write down equation underscore real. Then for substitution, I am going to use this syntax dot subs, then in the bracket we have values 1. Now here again the second equation will be equation underscore imaginary, then dot subs, then in the bracket we have vls values 1, and then finally this bracket will be closed. And then after that, obviously we are solving for what? Beta and phi. So again just close the bracket, and now we are storing these two values in a dictionary. So I will simply type dict equal to true true. So let me quickly summarize this, what I have done. So just from the beginning, right? I have first defined the vector loop equation, then I defined this A, B, C, D as symbols in Sympy, and then I declared them as real numbers. The same thing I did for theta, beta, and phi, right? This is one term iota equal to sp dot I, which I have defined here, so if it can be used later on. Then finally, let us come back to our position analysis. So here I have simply rewritten those vector loop equations, that is equation underscore real comma equation underscore imaginary. This is equal to, right, the function definition that we wrote here. So vector vec underscore loop underscore eq, then in the bracket we have theta comma beta comma phi. Now what I have done here, I have simply declared the values, all the values that we need to substitute into these two equations. So after that, after substitution, so let's go back to the substitution part first. So for substituting, I am simply taking this bracket, right, big brackets, then I'm simply typing equation underscore real dot subs subs, then in the bracket you have vals1. Same thing, same funda I applied to this equation underscore imaginary dot subs, in the bracket you have vals1, right? So after this, obviously I have used this command sp.solve. Sp.solve uses a range of techniques to solve for the values of beta and phi, but let us not go into very deep into those methods, and let us limit ourselves to this analysis only. So here we have this position value solved, right? After this, what we are going to do, we will simply print to check this position value, whether we are getting the required values or not. So let us simply run this program here and let us quickly see the output. So I will just simply click on this run code. Let's see what output we are getting. So here you can see that we are getting two values for beta and two values of phi. So this is exactly what we saw in our manual approach, right? There also we solved for two values of beta and two values of phi, because these beta and phi, they are actually functions of tan inverse. Now after this, let us say this. So beta underscore val. So what I'm going to do, I will pick up one of the value, because we know that later on these values, they have to be utilized for in solving angular velocities. So I'm simply picking one of the values, the first value. So let me just, okay, so let us start with the positive values of beta and phi. So I'm just simply putting 1. If you want to use the first value, this one, then you can use 0. So let's start with 1 only. Here then we have phi underscore val is equal to EOS pos underscore val, then just select value of phi. So you can check it out by printing these two values again. So what you are getting, so print beta underscore val, then print what you have, phi underscore val. So just quickly run this again. So now you can see that you can access the beta and phi value from the dictionary pos underscore val defined at this point. Once the position analysis is done, let us move to the velocity analysis. Now there is a catch here. See, till now the differentiation part was not into picture. So we were simply solving a set of trigonometric equations. But here what we are going to do, we are simply going to use the differentiation part. So for that, we need to define a new symbol that represents time. So here what I'm going to do, so define a new symbol. Let me simply type here, define a new symbol variable. Let me call this variable as t, that represents TIM with time. Now this is defined by t equal to, again, sp dot symbols, and then here we have t, and then here we have again real equal to true. So again I am seeing here that time t is a real number. Now it's very important. Initially, if you go into the position analysis, here we defined theta, beta and phi as symbols, correct? But here we declared them as real numbers. At this point, for velocity analysis, since we are going to differentiate this theta and beta and phi to obtain angular velocities. So we will define this theta beta as functions of time. Very important. So this is the difference between the position and velocity analysis. So we are going to define theta beta and phi as functions of time. Right. So to do so, what I am going to do, so theta will be equal to sp dot fun tiun sp dot function. Then in the bracket we have theta and bracket close, and then finally we are simply typing t here. So just be very careful with the use of brackets. Right, so again we have sp dot fun tiun function. Then again in the inverted commas you type beta, and then again in the brackets you have time t. Now similarly you define phi equal to sp dot function. Then again in the inverted commas you have phi. Then again this is your t. So once you have defined theta beta phi as functions of time, let us again differentiate the position equation to obtain the velocity equations. So again let us take this equation underscore real underscore position, and then equation underscore image underscore position. So these are real and imaginary parts, right? But here I am just using this new term equation underscore real underscore pos, comma equation underscore image underscore pos. So here we have theta comma beta comma phi. Now let's start differentiating these equations. So equation underscore velocity underscore real. So just to indicate velocity, I am just simply using this VL notation. So equation underscore L underscore real. Now we know that we have to differentiate the real part of the displacement or position equation. So here we have sp dot diff diff equation underscore real underscore pos underscore t. So we are differentiating with respect to time. You can appreciate this is the benefit of using the Sympy library. We are coding the equations as it is when we are doing all this analysis manually. So again here just differentiate the imaginary part as well. So it is equation underscore well underscore imaginary. So sp dot diff. Then again we have equation underscore image underscore pos comma t. So once we have differentiated these two equations, after this we will define the linear velocities. So linear velocities will be vp equal to sp dot diff. See, linear velocities are obviously the differentiation of the positions of the respective points, right? So we are going to calculate the velocity of point B. So this is simply what? d by dt of the position vector of point B, which is A. So here we will simply write down sp dot diff again. Now we are expressing everything into exponential format. So we will simply take A star, then sp dot exp. Now here see, I have already defined iota term as iota equal to sp dot I. So I am simply using this term here. So iota multiplied by theta and bracket close, and then after that finally what we have, comma t. Clear? So this is nothing. This is simply a vector is equal to a e to the power I theta. Now similarly velocity of point C we can write down. This is equal to sp dot diff. In this case we will simply use the triangle law, right? So using the triangle law, this will be basically d vector plus c vector So d vector, obviously it is making an angle of 0 degree with the x-axis. So if we take d multiplied by e to the power I of 0 degree, it will be simply equal to the magnitude d itself, right? And c vector is again written down in the exponential form. So c is sp dot, right? So c vector will be nothing. It is c vector, it is making an angle of phi with the x-axis. So c vector is the magnitude of c vector, that is c multiplied by e to the power I phi. So let me write it down here. So sp dot exp, then we have iota, so star phi, and then bracket close, and then again these are functions of time. So let me just write down here. So the resultant vector describing motion of C on C, this is simply equal to vector D plus vector C. So you can have a look at the diagram, right, that we discussed in the previous session, and you can simply infer from that the resultant vector that is actually going to describe the motion of point C, it is the summation of vector D and vector C. Now after this, once we have differentiated all the equations and once we have expressed the linear velocities, right, in terms of the parameters theta and phi, after this we will start making the substitutions. Now just remember, after this we need to again define symbols. So now I am going to define the angular velocities as symbols, omega AB, then omega BC, then we have omega DC. Now very important to note down here, right, these symbols in the substitution part, they should always come after the differentiation part. If you take this step before, then it will give you inaccurate values or incorrect values. It may also happen that the program is not going to run, right? The thing is that once you take this step before the differentiation part, then obviously they will be declared as real numbers, right? And the differentiation of these parts, it might become 0 and give you incorrect results. So always remember, this part we have to take later on, that is after the differentiation is complete. So after this we have sp dot symbols, and then you simply type omega AB, omega BC, right? So you are simply declaring all this as symbols, omega DC, and bracket close, and again these are all real numbers, so real equal to true. Now substitute all these symbols into the above equations, right? So just remember, for now I am not going to substitute the values. For I am simply substituting, that is replacing the d theta by dt term with omega AB, d beta by dt term with omega BC, and d phi by dt term with omega DC. Substitute in the above equations. So let me write down these equations again. So equation underscore well underscore real, this is nothing, this is equation underscore well underscore real dot subs. Substitution part will come here. Now after that, the curly brackets, right, you substitute this into a dictionary format. So sp dot, very important. So what we are doing, we are simply replacing d theta by dt with omega AB. So sp dot diff, then in the bracket you have theta comma t. So this term is replaced by omega AB, then again comma sp dot diff, sp dot diff. So let us break it here so that we can visualize it easily. So this is sp dot diff, then we have beta beta comma t, and now this will be replaced by omega bc, then again comma, then we have sp dot diff pi comma t. So this part will be replaced by omega dc. So what we did, it's very obvious. Here we differentiated these two equations, right, at this particular line numbers 55 and 56, and now after that in these two line numbers, right, we are simply replacing the differentiations of theta, beta and phi with omega ab, omega bc, omega dc. Now let me enter it here. So just close the curly brackets in the final brackets. After this, we will repeat the same thing for the imaginary part. So let me just copy paste it again. So this will be basically equation underscore well underscore image. So here what you do, you simply rewrite equation underscore well underscore image dot subs, and then in the bracket part you have exactly the same things which you wrote it down for the real part. Now once it is done, let us repeat the same thing for the linear velocity terms. So here you have vb equal to vb dot subs, and again in the bracket you have sp dot diff. Then here you have theta comma t, and here this is being replaced by omega a b. Now we know that the velocity of point B, it is simply the differentiation of right angle theta, correct? So here no other beta and phi terms need to be defined. So again vb is this, and vc will be equal to again vc, the equations we have already defined, dot subs sp dot diff, then we have phi comma t. So the velocity of point C, it will be mostly dependent upon the variation in angle phi. So we will simply replace sp dot diff, then in the bracket phi comma t with omega dc. So again the curly bracket, and then finally close this bracket. So here you have put it into dictionary form, right? So we are simply using the curly brackets. Now after all this terms have been defined, let us take up the values that we want to substitute. So if you carefully observe, now we need to substitute two new values in order to calculate the angular velocities of link BC and DC, and again the linear velocities VB and VC. So let me just pick it up from the top only. So let us copy this part. So this part will remain as it is because we are not changing the link lengths and the angle theta. So we will take up now two new values, that is beta underscore well, and let me just write it down. So beta underscore well we are taking from the previous calculations only, so we have already calculated. So we will simply take beta is beta underscore well, and in the same manner phi. So just note down that beta phi are right now symbols, we are replacing them with values, and then the last term is omega AB, right? So two new values, that is one for position and one for the angular velocity. So omega AB, it is provided to us, it is 10.5 radian per second. Now this part is done. Just put a comma sign in. Beta underscore. Right. Now the time is to solve for the angular velocities. So omega underscore sol, again we are going to invoke the sp dot sol relation. So sp dot sol, then after that we have two equations. One is equation underscore well underscore real, and then another equation is equation underscore well underscore imaginary. Right, now let us substitute the values into these two equations. So it is subs and vals 2, right? And again in the similar fashion, equation underscore well underscore image dot subs then vals 2. So after this, let us close this bracket here. Finally, we are calculating what omega BC and DC. So it is obvious that omega AB, it is provided to us in the problem. So we are simply calculating omega BC and omega DC, and then finally we will store this into dictionary form. So tick equal to true. So here our equation is complete. So just check out, right, if any bracket or anything it is missing here, right? And here we have, I think this one is fine, right? And then here we have omega ECDC. Now let's define vals 2, right? So this vals 2 is the new parameter that I have defined. Now after this, solution is done. Okay, so I think a comma is missing here. Just be careful with the use of brackets and comma. So now it is done, right? Now here you have to simply type print omega underscore sol and just check for the solution. So now here omega underscore BC underscore well. So let us separate out this solution omega underscore sol, then just pick up the solution, access the solution from the dictionary. So it is omega BC, and now here omega underscore omega DC underscore well, right, is equal to omega underscore sol, right? So we are simply accessing the dictionary, nothing is omega, right, DC. Now here let me just run this code and let us check out what solution we are getting. So now you can see here, so we are getting these values of for angular velocity omega BC and omega DC. So you can just correlate these values or match these values with the manual solutions, and so we are actually exactly getting the same values here, right? So another point to note down here is that we already filtered and we have already taken the positive values of beta and phi, right? If you take the first value, right, the other values of beta and phi, so you will get a different value of angular velocities for the links BC and DC. So now this is done. Then let us solve for linear velocities. So once you have obtained the angular velocities, solving for linear velocities, it is simple substitution, nothing else. So solving for linear velocities, so VB underscore real well, right? Now this is nothing, this is the absolute value of the complex equations that we have defined before. So first of all, you just substitute VB dot substitute vals 2, right, and just take the absolute value. Here also you have VC underscore well is equal to SP dot again absolute. So obviously these are all complex numbers, so we need to take the absolute value. So let us substitute VC dot subs, then here you have vals 2. Now here if you note down, right, in order to calculate the linear velocity of this point C, you also need to have the angular velocity of link BC. So let us put it here, subs of, here you will have omega, right? So omega solution you have already got it here. So what you have to do, you simply put omega sol and 0. Okay, so this is what this is, you are simply selecting the value that were there in the right dictionary omega underscore sol. So after this, what you do, After this, you can simply print VB underscore well and just check whether you are getting correct values or not, right? So see, this is very good if you code such kind of equations into any sort of programming language, be it Python or MATLAB. So you can actually automate the entire process, and you can just verify your results, and you can make these iterations for different values of theta, phi, beta, and the link lengths. So after this, let me just again run this code. So now you can see here, these are the values of point B and C that we are getting. So you can see here, this is again, just remember this point that right now these values are in mm per second, right? So in mm per second, very important. So you can see here that, and the velocity of point C is 0.4 meter per second. So this is exactly what that we got with manual calculations, right? Now we will begin with the acceleration analysis. So let us see what to do in an acceleration analysis. So it's pretty much similar to what we did for the velocity analysis. So just to be cautious, what we are going to do, we will again introduce the symbol t as time. So this is again t, then comma real is equal to true. Then again we are going to define theta, beta and phi as functions of time. So let us take it from the top only. So just note down, right? So why I am redefining this theta, beta and phi as functions of time? Because when we were taking this VAS2 value, right? So we already substituted this theta, beta and phi with numerical values. So since for acceleration, we are going to perform the differentiation again. So that's why I am reintroducing this theta, beta and phi as functions of time. Now after this, we are going to take the position equations again. So since we are using the position equations again and again, that was the reason I defined this position equations as a function in the beginning. So again we are going to take VEC underscore loop underscore equation. So here you can define the velocity expression as well and take the velocity expression, but just to maintain consistency, I am taking the position equations only, and I am going to differentiate this position equations twice to get the acceleration. So again we have here equation underscore real. This is again sp dot diff, right, and equation underscore real underscore position. And now we are differentiating twice, so it will be comma t comma 2. So this will be my real part. Then again let us differentiate the imaginary part. So again sp dot diff, then we have equation underscore image underscore pos, right? Then again we have t comma 2. So just remember, this is my imaginary part. So for differentiating ties, right, you just use this numeral after this variable t. So it will be t comma 2. Now after this, let us define the acceleration terms. So acceleration terms will be AB, right? And obviously acceleration terms is differentiating twice the position vector of point P. So it will be sp dot diff, then here you have a multiplied by xp dot exponential, right? So it's nothing, it is a e to the power I theta, and then we are differentiating this twice. So a sp dot exponential iota multiplied by theta, right? Now let us close this, and this is t comma 2. Now in a similar manner we will calculate the acceleration of point C. So acceleration of point C is double differentiation of the vector C. So it will be simply C. Then we have sp dot exponential. Then here iota in place of theta, we have to simply replace this with phi. So we know that again we need to substitute, right, the angular acceleration symbols, right, in place of double differentiation of the angles theta, beta and phi. So we will repeat the same process what we did for velocity analysis. Only thing, here we are going to replace the double differentiation terms instead of the single differentiation terms. So it is now alpha dc. So we will introduce again new symbols. So alpha AB, alpha BC, alpha DC. So obviously alpha AB, alpha BC and alpha DC, they represent the angular accelerations of links AB, BC and DC. So it is again sp dot symbols. Then in the bracket we have alpha AB, then alpha BC and then we have alpha DC. So put these three into inverted commas and then again I am defining that all these are real numbers. So this is just a precaution that it doesn't read all these symbols as imaginary values. So it's important to define that all these are real numbers. So real equal to true. Now after this we will simply make the substitution. So we are going to replace the double differentiation terms via the symbols. So here we have equation underscore real, then substitute, right? Now again take the bracket, then take this curly bracket, just enter and just type it here. So first we will replace d2 theta by dt2, that is double differentiation of theta, with alpha AB, then double differentiation, that is d2 beta by dt2 with alpha BC, and same of y comma t comma 2. Right, so here we have theta, and here we have beta, and here we have phi, and this will be replaced with alpha DC. Now since we have reintroduced theta, beta, phi as functions of time, so we will again define the angular velocity. So we will simply take this from the top only. So here we have already defined these terms, so we will simply take these terms. So let us put it before the acceleration term just to avoid any sort of confusion. So just be careful. After defining the acceleration equations, what I am simply doing, I am simply replacing the d theta by dt, d beta by dt and d phi by dt terms with omega AB, omega BC, omega DC, and d2 theta by dt2, d2 beta by dt2 and d2 phi by dt2 with alpha AB, alpha BC and alpha DC. Very simple. So this substitution is important. Okay, so before this, it is again better to introduce these also as symbols. See, after differentiation is over, it is always better to reintroduce these terms as symbols. Now this is done. Now let us repeat the same thing for the imaginary part. So I'm going to just copy paste this part here, and then I will simply erase this real and type image. So after the substitution is done, now is the time to substitute the values, right? So let's first do the same thing for these AB and AC. So let me copy it from the top. Right, so because it's a simple repetition of the things, so let's take it from here, right, and now let us place it here. Let's keep it like this. Let's close the bracket. Okay, so the same thing I'm going to repeat here also. So just copy paste this part. Okay, just put a comma sign everywhere, otherwise it will give us errors. So just quickly put a comma sign. Now the same terminologies it will be pasted here. After this substitution, now it's time to define the values that we want to substitute. So again, if you see the values for the input parameters, right, that will be modified again. So this Wells dictionary, right, I am now going to rename it as Wells 3, right? So you can actually rectify it and use the same name again and again, but just for better differentiation, right, to avoid any error, right? So what I'm going to do, will simply use a new name. I will call it Wells 3. And now let's see what other parameters will be added to this dictionary. So obviously now beta well and phi well, they will be there. Omega AB will be there. Apart from this, now we have values for omega BC. So we will add omega BC underscore well, right? So this value we obtained here, if you observe. So without substituting the angular velocities, it is not possible to calculate the linear acceleration. So these two values I have already computed above. Now I am going to substitute those values here, right? Then we have omega DC, which is again omega DC underscore well. Alright, so after defining the angular velocity terms, now I have alpha AB. So let us take it as minus 26. Now after this Wells 3 is defined, right? So now the next thing is very simple. You have to simply substitute it for solving the angular acceleration values. So solve for angular acceleration first, and then we will solve for the linear acceleration. So solving for angular acceleration, it is very easy. So let us alpha underscore solution solve. Again we will invoke sp dot solve. We have again two equations to solve for. So one is the equation underscore acceleration underscore real. So this will be equation underscore acceleration underscore real. Now we will substitute Wells 3. Now here this is comma. Then again we have equation underscore acceleration underscore imaginary. And then we will substitute Wells 3, right? Then the bracket will be closed, and then finally we are solving for alpha BC and alpha DC. So we will need to specify what we are solving for. So alpha BC, alpha DC, and again the bracket closed, and then finally dict equal to true. So the use of bracket should be accurate, right? So just keep in mind that these two equations we are putting it as a list, right? So you can see that we are using these square brackets here, right? And then outside we have simple brackets, and then when we need to put these things into dictionary form, then we are simply using the curly brackets, right? So here it is not required. Here mainly the square brackets are there. So here after this subs of Wells of 3, so this should be closed, and then in the end you can simply check the angular acceleration solutions, right? So it will be print alpha underscore solve, right? So but before checking, let us solve for linear accelerations also. And now this is first is AB underscore well, right? So again it is absolute of sp dot absolute of AB. So what was your AB? So AB was AB dot subs, right? Again we need to substitute the values, so just don't forget this point. So subs of Wells of 3, correct? So these values we already have, but apart from this we also need to substitute the omega values, correct? So omega DC, they are there, right? If they are there, then let us simply substitute alpha values. So alpha underscore sol, then obviously just access the corresponding value from the dictionary, and this is ab underscore val is equal to this one, right? And now similar expressions you will write for calculating the linear acceleration of point C. So you have to simply replace AB with AC. Rest of the things, they will remain as it is. And finally it is print AB underscore sol, and then we have print AC underscore val. So let us run this code and let us see whether we are getting our solutions or not. So once you have defined all these expressions, so just be careful with the use of commas, right? So if in any case I am missing comma after defining any parameter value, just put it there, right? Put all the commas, right, carefully, and then after that you simply run this program. Let us check for the values of alpha BC and DC. So you can see that how quick it is, right? So alpha BC and alpha DC we have obtained. It is alpha BC is 32 radian per second square and alpha DC is 77.3 radian per second square. So these values you can check, right? These are exactly matching with what we obtained before. And now the linear acceleration values you can observe here. For linear acceleration of point C, the value is 5.2 meter per second square, and for linear acceleration of point B, it is 5.6 meter per second square. So you need to convert it from mm per second square to meter per second square by dividing these two values by 1000. Let me just summarize that what we did. So we simply solved a 4-bar mechanism for linear velocities, linear accelerations, angular velocities and angular accelerations using the Python Sympy library. And we use the Sympy library just to comprehend all the analysis in a better manner, because we as you can see that we have coded the equations as it is, right? And now we have solved the equations exactly in the same sequence that we used to do before. That is, first start with the position analysis, then go with the angular velocity and linear velocity analysis, and finally go with the angular acceleration and linear acceleration analysis.
So after the analysis for a given set of values is complete, now you can repeat this analysis for some different values of the input parameters. So let us take the value of theta now as 100 degree. So just make this substitution in the vals 1, you change it to 100 degree, right? Similarly, you repeat it for vals 2 and vals 3 as well. And here you just check it that I also again change the value of acceleration, angular acceleration of link AB from minus 26 radian per second square to plus 26 radian per second square. Now if you click this, so you can observe the changes in the linear velocities and accelerations. Now you can see here the linear velocities of point C, they are changing significantly, right? So similar iterations you can perform and you can observe the different values of velocities and accelerations. With this, I would like to end this session. Thank you.